In this module, I'm going to introduce the topic of induction, mathematical induction. Uh, I'm going to use the ideas from this in the next module where we are going to talk about recursion. These two concepts are very closely related to each other. A few things to remember, especially about this module. I want you to solve as many problems as possible. I want you to go through each example that I have on the slides, use it to see what we are doing in each step and how we are using these steps to come up with the final conclusion that we want. Induction is known to be a tricky topic. It's partly because it appears like circular reasoning, and you need to be careful to make sure that your reasoning is not actually circular. The way you can do that is you can solve as many problems as you can. There are a lot of problems in the textbook. You can look through that, as well as we will solve many problems in class as well. You have solutions to odd problems in the textbook. I want you to make sure that you go through those solutions to a point where you are like, oh, this is so straightforward that I don't know why the professor says this was confusing. This is going to be the key to understand mathematical induction. Uh, Another thing, mathematical induction is not just important for this class, it is something that is important for lots of other things that you might come across in the future, and that's why I have put this slide before actually getting into the meat of what mathematical induction is. So let's look at this example, this supposed proof. We want to prove that every even integer greater than 2 can be written as sum of two primes. So let's look at an example. Let's look at the proof. Supposed proof. 4 I can write as 2 plus 2. 6 I can write as 3 plus 3. 8 I can write as 3 plus 5. 10 I can write as 5 plus 5. 12 I can write as 7 plus 5. 14 I can write as 7 plus 7. Then 16 I can write as 11 plus 5, 11 plus 7, 20 is 13 plus 7, and so on. From this, I want to conclude that this statement is true for every integers. Now, I'm going to ask you to pause the presentation here to think about what you think about this proof, collect your thoughts before you continue. Now, I imagine that most of you are like, this is stupid, this does not make sense, because we proved up to 20. Yes, it looks like a good pattern, but I have no idea how to do 22, 24, and so on, and it's not clear whether the number 5,792,000 can be split as two primes. Clearly, this is not a valid proof. This is not a valid proof. And the reason is, of course, we stopped at 20. We don't know what happened afterwards. Our goal in mathematical induction is to be able to get proofs of this type in some sense, but to make it work in all possible integers, and that's basically what we are trying to do. Once again, we have reached the check before you go ahead slide. The key thing I wanted you to get from this part was making sure that you realize that checking a property for several integers doesn't prove it for all integers. If you have checked it for a dozen, 100, million, it does not necessarily mean that it is true for all integers. In fact, there are several interesting properties where we have been able to show those properties hold for lots of integers, even of the order of millions, billions, but we don't know whether those statements are true for all integers.